Well, welcome to the 8.7 Notes for Calc AB. We're going to be looking at revolutions and volumes of revolutions. So I want you to imagine that you had some curve. And if you look at the area underneath that curve, that's this yellow part here. And then you take that and you revolve it. You rotate it around. Well, what happens is as you rotate things around, is that you're making a circular motion. And some of the circles are smaller than others. And then some of the circles are very, very large. It really depends on how far away the edge of a curve is from the axis of revolution. We could call this line right here. This could be our axis of revolution. Okay, our line of revolution. And depending on how far away the edge of a curve is from that, will tell you if you're going to get a very big circle or some very small ones. Now, this whole region would actually all be kind of circular in shape, right? And some of them, again, are smaller as we go all the way around. And then as we get farther away from the x-axis, we get bigger ones. But we can take this and we can slice these revolutions up into very, very small little cylinders. Very, very tiny cylinders. I'm going to erase some of my random markings here so you can see the cylinder better. Now we want to make these cylinders so thin that they essentially, that their width here, their height is almost zero, okay? We want to basically take up this solid here that we're forming, this 3D shape, and we want to split it up into an infinite number of these very tiny little cylinders. And really what they start to look like almost more is like circles, to be honest, which is like the base of that cylinder if the height was essentially approaching zero. And so that's really what we're going to be doing here. And so the interesting thing here is if we want to find the volume of whatever this funny look shape is, I kind of think that this shape would maybe start to look a little bit like a vase. I think it's in my mind kind of what it starts to look like. I don't know if that makes sense to you, like kind of a vase on its side. If I wanted to find the volume of this, what I could do is I could find out the volume of each of these tiny little cylinders and then add them all up. Well, the idea of adding things all up, remember, is really the idea of an integral. Now, people often call these tiny little cylinders disks, okay? These tiny little cylinders people can call disks because they're just so thin. They really start to even just look like circles. And you might remember that the way you find the volume of a cylinder is pi r squared, which is the circular base times the height. The height being this part right here. We could also think of that height as our change in x. And we want that height to essentially approach zero. Okay, so that's what we'd really like because we'd like to have as many disks here as we can. And then what we'd like to do is we'd like to find the pi r squared, and I usually pull that pi out front, for each of these cylinders, and we're going to add them all up from A to B. Now you might notice pi r squared looks like a circle. So it's like the formula for the area of a circle where the height of each of these disks or their width is very, very small. So let's try a few examples. Here's the first one. We want to find the volume of a solid that's formed by revolving y is equal to 4 minus x squared, which is a parabola, around the x-axis on the interval from 0 to 2. So basically what we're doing is we're going to take this portion right here. We're looking on the x interval from 0 to 2. And we're going to take this and we're going to rotate this around the x-axis. And, let me go back really quickly up here. It is important that we represent that radius as some function, in this case in terms of x, because I want you to notice that the radius changes. The radius will change depending on where I am on this function. And that's going to be true on this one as well. What's going to happen here is we're going to basically be slicing out circles here. Here's a radius of some circle and rotating it around. Some of these circles are going to have shorter radii. So we're going to use the form of the definite integral from 0 to 2 of pi r squared, pi, and then the radius squared. Now what the radius is the height of your function. And notice it changes. The radius can be different heights at different x values. So it is basically the equation of the function. That is the radius. And then we can use the calculator on this one because of the directions that they gave us. So I'm going to do the definite integral from 0 to 2. And then make sure that you take your expression and square it. This would be a 4 minus x squared, but then quantity squared as well. So I want to make sure that this 4 minus x squared is the radius, and I want to square that. And I get 256 over 15 for my volume. Now, certainly we could do this by hand. I would probably recommend you FOIL it out, expand it out, and then use the power rule. All right, it's the most important thing for us right now, to be quite honest, is to make sure that we really know how to write the equations and to make a good diagram and a good picture. That's going to be really incredibly important because we can always integrate. Okay, we know how to integrate, and often these can be used with a calculator. Sometimes you're just really writing the equation, but we really need to make sure that we know how to draw a good picture and to write a good integral expression. Okay, so I'm looking at y equals 2x squared. Something like that. And I want this to be bound by the line y equals 0, which is this horizontal line here along the x-axis. The line x equals 0, which is, wow, doing awesome, which is my y-axis. And x equals 2, which is a vertical line. So this is my region that I'm looking at, bound by all three of these right in here. But now what they want to do is they're going to tell me how I'm going to rotate this. I might need to draw my diagram more than once because I have part A and part B. So initially I'm going to rotate this around the x-axis. So because I'm rotating this around the x-axis, these are my radii. The radii should be drawn from the curve all the way down to the line of rotation, or the axis of rotation. And so my radii really are just the height of the function y equals 2x squared. So volume will be found by pi times the definite integral, in this case from 0. Remember, this was the line x equals 0, and this was x equals 2. So from 0 to 2 on my x values of 2x squared, which is my radius. Radius needs to be squared, so pi r squared dx. This is going to give me my disk. We could then put this into the calculator, and we'll get 128 pi over 5. Or if you prefer, around 80.425. Your choice. Both answers are great. Now this changes a little bit when I change the way that the line is rotating. Okay, so I do want to be careful here to always read about where am I rotating this about, because it does change the strategy. Let's try this again. So I have the line y equals 2x squared. And then I'm using y equals 0, x equals 0, and the line x equals 2 as my boundary. So the trapped region between those is right here. Now, interesting enough, this time I'm rotating this around a vertical line, around x equals 2, like this. My radii need to be drawn from my curve to the axis of rotation, which I want you to notice. My radii are now drawn horizontally this time. This would be the radii, like that. So because my radii are horizontal, I cannot do this dx. I have to do this dy. So this will kind of bring you back a little bit to what you did in 8.6. where if we are taking horizontal slices, we needed everything to be done with respect to y instead of with respect to x. that is going to change my setup. Because these, since this was dx, these were x values and my input variable was x. If I'm now doing dy, then these have to be y values. I need my lowest y value to my tallest y value. Well, I don't necessarily know what that tallest y value is off the top of my head. To find it, I'm going to need to see where these curves intersect. So 2x squared would intersect the line x equals 2. Well, actually, since I have an x value, I will put a 2 into this equation to find the y value. I had to think about that. Square first, then multiply. Y is 8. So this goes from a height of 0, I can tell that from the diagram, up to a height of 8. Now, because this is dy, I also can't write my equation with an x variable. So my radius is going to be formed by comparing the length between my curve and the axis here. And so the way I'm going to need to write this needs to have this in terms of y. So I'm going to divide by 2 and then square root. Now remember, when you square root both sides, you get a plus or a minus. Well, that's to show the two. This is the minus side. This is the plus side. I'm using the plus side, so I will only use the plus here. And what a lot of students do, and this is wrong, okay? This is wrong. What a lot of students do is they just write this, and they think they're good. That's not correct. Here's why that's not correct. If I just write that formula, that will take me to the y-axis. That would give me lengths from this function. Well, I guess it's not. It's in terms of y, but it'll give me lengths from here to the y-axis, which you'll notice those are not the radii. Okay, so if I just use an equation by itself, that will give me to whatever axis we're doing this with respect to. Notice I'm actually needing to be between the line x equals 2 and my curve. So what I have to do, and this will kind of remind you a little bit of what we did in our last lesson, is I need to do right minus left. This is actually a preview of something we're going to talk about on the next page called the Washer method. And that's going to be how I'll get the radius squared. Remember, we do still want to square the radius. So this will be the volume to be found by pi times the definite integral from 0 to 8 of the equation on the right, which is 2, minus the equation on the left, which is the square root of y over 2 dy. Quantity squared. Quantity squared. Do not think that these squareds should be distributed, not when you have a minus sign. You would then enter this into the calculator. I would just recommend entering in exactly how it looks, including the pi, by the way. You can just type pi in the front. Oh, yeah, and I guess on my last one, I want to make sure, because I don't think I typed that on the last one. Ooh, fail. There's a pi there. Okay, so I'll show you on this one how you can type it with the pi. So the pi button, I don't know if you saw that, it's right here. And then I can do the definite integral. In this case, it's from 0 to 8. Remember, I have to have y values because this is dy. And then it was the quantity 2 minus the square root of y over 2. This needs to be squared. Okay, that whole expression for that radius, and then dy. I'll get 16 pi over 3. And I won't forget my pi this time, like I did on example 1, which was awesome. I wonder if how many of you noticed that and were like yelling at the video going, Miss All, you messed up. Okay, example 3, we want to find the volume of the solid form by revolving this shape around the axis. We do not get to use a calculator. So why don't you start by seeing if you could draw this and maybe get a sense, see if you can set up an integral, and then we'll compare. Okay, well, the square root of 16 minus x squared is kind of interesting. You will probably want to start to recognize what this is. If I take this shape and I square both sides to get rid of the square root, and I combine my variables on the other side, you might notice that this is a circle. Now, if I get y alone, if I kind of go backwards and I get y alone here, and I square root both sides, you will remember that when you square root both sides, you get a plus or minus. I didn't have the plus or minus. I just had the principal square root, the positive square root. I just have the top half of the circle. This circle has a radius of 4, which is the square root of 16. But I only have the top half of it. You will want to recognize this shape. Okay, so y equaling the square root of some number squared minus x squared, that is a semicircle. This is not a very great job of me drawing a semicircle, so I'll try again. Now we want this to be revolved around the y-axis, so that's troublesome for me. And x is going to be between 0 and 4, so we're looking at this. Revolving this portion around the y-axis. And since my radii have to be drawn from the curve to the axis of rotation, I'd like you to notice that this is another problem that's dy. So I'm going to do pi radius squared dy. Now my y values, these have to be y values because it's dy, are from 0 to 4. In this instance, it's the same as the x values, but that's not super common. And I also want this to be with respect to y and not x. So if I go back maybe to here, if I get x squared isolated instead of y squared isolated, and I square root both sides, x would equal plus or minus the square root of 16 minus y squared. That's because there's two sides. There's the positive side right here. There's the negative side of x, of the x-axis right there. We want the positive side, so I'll do the positive square root of 16 minus y squared. I do not get to use a calculator here. Now the squared and the square root will cancel out. I cannot cancel the square root out with this square because of the minus, but the outer one will cancel out. So this will be pi times the definite integral from 0 to 4 of 16 minus y squared dy. And now I'm going to pull this pi out front, and I'll use the power rule. So this would be 16y minus 1/3 y cubed, and then evaluated at 0 and 4. So this would be pi times 16 times 4 is 64, minus 4 cubed is 64, but divided by 3, so 64 thirds, minus 0 minus 0. So I'll get pi times, let's see, I do want to get a common denominator here, so I'll just take 64 and multiply it by 3 on the top and bottom to get 192 thirds minus 64 thirds. And when I combine that, this would be pi times 128 thirds, which I think you're going to see more commonly written as 128 pi over 3. And so anytime that your radii or horizontal, you need to do this dy. These have got to be y values, and you're going to have to make sure that this variable is a y variable. Now, you might remember me saying that part B was a preview of something coming up. Here's what it is. It's called the washer method. The washer method, a washer is like a disc, but it has a hole in the middle. You can identify the washer method because what you'll see is that there is white space or non-shaded space between a shaded region and the axis of revolution or the axis of rotation. How do you spell axis? There we go. So notice that for this shaded region, it does not touch all the way down. We're revolving it around the x-axis. It doesn't ever touch the x-axis. It can even touch once for part of it. But if it ever has that gap, then what happens is as you draw this, we could think of this as two radii. There's one radius for this outer edge of this washer. That's going to be from the curve that's farther away from the axis of rotation. And then there's a second radius from the closer curve, and that radius, notice, creates this empty space. And because there's more than one radius, here's how our region looks. Our region is really going to be volume. It could be found by, what happens is, if you do pi r squared of just the big radius, quantity squared. What that would do is that would give you the entire cylinder colored in. But we don't, we have this empty space. So what you have to do is you have to subtract off the small radius quantity squared. And that will subtract off and make sure that's squared. And then in this one, it's dx. I'm going to rewrite this. I'm worried you can't see that. So the washer method is the volume is equal to pi. We're still making cylinders. Of the definite integral from a to b of the big radius quantity squared, which is too much volume. And we'll remove the smaller radius, the one that's closer to the axis of revolution or the axis of rotation quantity squared, dx. So this one we do get to use the calculator, but I do want to show you how you could graph this without a calculator. You could look at this and tell it's a quadratic and that it's opening down, but you might still have some trouble graphing it. So it might be helpful to figure out on this one perhaps where maybe the vertex is, or perhaps where it crosses the x-axis. It's kind of up to you, but if you want, you can do that. I know that this one's a line. Maybe I'll graph that one first. 1, 2, 3, 4, 5, 6. Slope is up 1 and over 1. It's kind of going off my shape a bit, off my graph. So there's my line. Now, if I want, maybe if I set these equal to each other, that might help as well, because if I find the point of intersections, that might help me graph. I'm going to group everything over together on the right-hand side. And then if I factor this with the greatest common factor, x is equal to either 0 or -3. So these are going to intersect when x is 0, which is at the point 0, 6. And also when x is -3, which is right here. And I know it's quadratic's opening down, so it looks something like this. Now you could find more about this quadratic if you really wanted to. Here's my region that's bound by these two graphs. And I want to find the volume if I rotate this around the x-axis. So I'd like you to notice the empty space in between my shaded region and the axis of rotation. In fact, if I draw in a radius from the top of this curve all the way down to the bottom, you might notice how I leave my shaded region all the way down to the axis. In fact, really, there's two radii here. This is the big radius. The curve that's closer to my axis of revolution would be the small radius. And so if I'm going to find this area or this volume formed by this revolution, this is the washer method because of that empty space. So the volume is equal to pi, and this started at an x value of -3 and ended at an x value of 0 from those points of intersection. And I want the big radius quantity squared. Well, the big radius was formed by f of x, the quadratic. I need to square that function by itself. I need to remove from that the line, which would be squared by itself. Be careful, make sure that you are squaring f before you subtract the square of g. You do not want to square the entire expression with a minus. You're squaring each radius separately. And that is important. You could then put this into the calculator. You'd get 243 pi over 5. And we may have had that answer already today. I don't remember. Not quite. Close to it. Now, this is the same set of equations. Okay, so I have the line x equals 6, which is a y-intercept of 6 and a slope of 1. Like that. And then I have the quadratic that's opening down, and those intersect at 0 and -3 and looks something like this. I don't really know how high up this vertex is, and it doesn't really matter. Now this time my line of rotation is the line y equals 3, which is right here. And sometimes people wonder, is this still washer? Because right here they do touch. The answer is yes, because look at the rest of this region. See the white space? This is still the washer method. There are still two radii, one from the top curve and one from the bottom curve. That's another way to identify radii here. And remember, the radii go from the top curve down to the line of revolution or the line of rotation here. And if there's two of them, that's washer. So volume would be pi times the definite integral from -3 to 0 of the top radius, now a little bit different from our previous one. If I just say f of x, that has to go the length all the way down to the x-axis, which you'll notice this one actually doesn't go all the way down to the x-axis. It stops at 3. So the way I would write my big radius, because I want the big radius squared here. If that radius does not go all the way down to the x-axis, you do top minus bottom to describe that radius, and that's inside the squared. That can also happen, by the way, for the small radius. Remember, we want the small radius squared here. But notice that for my line, if I draw that radius, it's not going all the way down to the x-axis. And so I need to do top minus bottom. It stops at 3. So this would be pi times the integral from -3 to 0. The top curve, we are using f of x for. So this would be f of x minus 3 quantity squared, because you stop at the bottom curve of 3. I know you might be like, it's not very curved, it's straight, but we can call it that. And then minus the top curve, which is g of x, minus the bottom curve of 3. Quantity squared dx. And if you then evaluate this, you would get 108 pi over 5. Now the next pages have extra practice. And so you can see the answers are on here, but I am going to go through them for any of you who think it would benefit you to just have a little bit of extra practice, including drawing some of these, because quite often you have to draw them on your own. And so I encourage you to pause the video and try them on your own before you move ahead and look at the work. So this would be a semicircle, the top half of a circle. The radius of the circle is 3. This is really could be rewritten if you do a little algebra here. Is x squared plus y squared equals 9. So we have a circle with a radius of 3, but I'm only using the top half of it. If you need any more kind of reinforcement with that idea, go back and look again at example 3 from our notes. So this looks something like that. And I am revolving this around the x-axis, which tells me that this is going to be dx. In fact, if I draw in radii, notice that they are perpendicular to the x-axis. So that's another way to see that these are dx. Here are some examples of some of the radii. So I'd also like you to notice that my shaded region goes all the way to the x-axis. So this is the disk method and not the washer method. My area here starts, my shaded region starts at -3 and goes all the way up to +3, and I want to do pi times the definite integral of my radius squared. And my radius could just be communicated by the equation. Because this one doesn't tell us to use a calculator, I'll do this by hand. The squared and the square root cancel out. And I'll use power rule to integrate. So I'd get 9x minus 1/3 x cubed, all of it times pi, and then evaluate it at 3 and -3. So then if I plug in a 3, I'd get 27 minus 3 cubed is 27, divided by 3 is 9. And I'll subtract off, I'm going to evaluate this with a -3, and I'll get -27. And when I plug this in, I'll get -27 times the -1/3, which will be +9. If I do a little distributing, just be super careful here. Let's see, I guess I'll combine first. I would get 18 minus a -18. And my final answer would be 36 times pi. All right, for the next one, we want to find the solid. The volume of the solid, region bounded by y equals secant of x, and the x-axis from -pi/4 to pi/4, and we're going to revolve it around the x-axis. You might have a little trouble graphing secant of x. It might help. We're going from, by the way, -pi/4 to pi/4. It might help a little bit if you remember what cosine looks like on this region, which is something like this, because secant is the reciprocal of that, which would look like this. So we are bound by that and the x-axis. So the shaded region is between my graph of secant and the x-axis here, like this. And we're revolving this around the x-axis. Well, this one is going to be something that would be a disk because our shaded region goes all the way to the x-axis. And so I'm going to do the volume as doing pi times the integral of the radius squared dx. We're going from negative pi over 4 to pi over 4. The radius would be secant of x, but we want that squared. Well, that's kind of nice because the integral of secant squared is tangent. So this is pi times the tangent of x, evaluated from negative pi over 4 to pi over 2. So this would be pi times the tangent of pi over 2 minus the tangent of negative pi over 4. Oops, I think I wrote this wrong. This is a pi over 4 here, and here, and here. I'll make those 2's look like 4's. So this would be pi times tangent of pi over 4 is 1 minus the tangent of negative pi over 4 is negative 1. So I would get 2 times pi. Last one. I want to find the volume of the solid resulting when the region of 1 minus y squared. So 1 minus y squared, notice that's in terms of y. That's kind of interesting. 1 minus y squared is a parabola that's opening sideways like this. And this is also bound by this one's bound by the y-axis. So here's the region. And we're revolving this around the y-axis. So notice how the radii are going to be horizontal slices. So this is going to have to be done dy instead of dx. My equation's already dy, which is kind of nice. If I want to figure out where these heights are at, I should set right here. I can actually take this for a minute and just plug this in and set this equal to when x is 0, because that's where that would be on that axis. And so y squared is 1 and y is plus or minus 1 when I square root both sides. So this would be the definite integral from negative 1 to 1. Now remember, I'm doing pi radius squared. There is only one radius. This is not washer, this is disk, because the shaded region goes all the way to the axis of rotation. And so this would be 1 minus y squared quantity squared. Now, in order to integrate this by hand, I'm going to expand out this expression. So I'll FOIL it times itself. This would be 1 minus 2y squared plus y to the 4th dy. And then I would integrate this by using the power rule. So I'd get y minus 2/3 y cubed plus 1/5 y to the 4th. And then this would all get evaluated at negative 1 and 1. What I end up with is pi times 1 minus 2/3 plus 1/5 when I evaluated at 1 minus negative 1 plus 2/3 and then plus 1/5. Watch your powers here with those negatives. And then to finish this off, I would go ahead and get a common denominator to evaluate all of this to get 16 pi over 15. And this is a power of 5. So that changes things. That makes this a negative 1/5. And that is the end of our video.